in the chat, and I'll keep an eye on that as well. Other than that, I guess we'll take it away. So Armal did his PhD at University of Washington and is now an N3AS fellow at University of Minnesota and at Berkeley. He's going to tell us today about collective neutrino flavor mixing in core collapse supernovae.
Thank you.
So take it away. You should be able to share your screen. You got it? Okay.
Yeah. Do you guys see the screen?
Yeah.
All right. Perfect. I'll put in presentation mode. Yeah. Hi, everybody. My name is Rrapaj. As already mentioned, I'm an N3AS fellow, which is a network for neutrinos, nucleus of physics, and symmetries. Currently in the University of Minnesota, joint position with UC Berkeley. Today, I'll be talking about neutrino flavor oscillations in supernovae, and try to give a many-body explanation of how these oscillations behave and what's new when you do many-body treatments. So, as a quick introduction into neutrinos, there are 3 flavors being produced in weak reactions. We have the electron neutrino, mu neutrino, and tau neutrino. After they're produced, they actually evolve in vacuum in their mass eigenstates, which are 3 masses. The mass eigenbases and the flavor eigenbases are unfortunately not the same. Therefore, there is a flavor oscillation in vacuum after they're produced. As such, for instance, the electron neutrino, which would be interesting for us for supernovae, it's the superposition of these 3 mass terms. We don't know the exact value of the masses. It's a current area of research, but we know that 2 of them are close to each other in value and 1 of them is farther apart. When 1 further apart is a higher mass, it's a normal hierarchy. Otherwise, we call it inverted hierarchy. We have some calculations, some numbers just for the difference of the square of the masses, which is the order of 10 to negative 3 and 10 to negative 5 electron volt squares. So indeed, they are very light particles. Let's take, for example, an electron neutrino, which is produced somehow in, for instance, a neutron neutron. You have the electron flavor, which is superposition of 3 mass eigenstates. Think of this as a wave superposition that's shown here as a wave packet. And as it keeps traveling due to superposition of these 3 different modes, it will appear first as a neutrino, then perhaps mu neutrino, then a different flavor, and so on and so forth. This is the oscillations that we see in vacuum. In dense environments, we also have a matter background of electrons, and this gives rise to more complicated flavor oscillations. Here's a flavor evolution equation of an electron flavor, where X is a superposition of muons and taus. In these calculations shown today, I'll only focus on 2 flavors, which gives enough qualitative features to understand flavor oscillations in these environments. We have the mass term, which comes from the mass eigenbases, and we have also force scattering with matter, which comes to first order in GF. I'll go through this slightly later. And theta is the mixing parameter which shows up because the 2 bases, the mass eigenbases and the flavor eigenbases, are not one and the same. This will give rise to the famous MSW mechanism. Why do we care about neutrinos? We care about them because they carry away most of the binding energy, more than 90%, as we all know, of the binding energy of a progenitor of a supernova core collapse, which is 10 to the 53 ergs. We produce all flavors. Here we have schematically shown in the radial profile of a supernova. We have neutrinos being emitted and leaving the star. They are important because they interact with the matter. They can reinvigorate the shock wave. Also, another important effect is the nucleosynthesis, because they will change the neutron to proton ratio. So therefore, they will impact the seed elements that give rise to the heavy elements introduced in the supernova process. This is a very complicated picture itself. We know simulations are very hard. On top of that, I'm adding another complication, which is the fact that not only neutrinos propagate through matter, but also they will oscillate into each other, into these 3 flavors, making calculations even more difficult. As such, let's try to simplify things so that we can have some qualitative understanding. So today, I'm not going to present a supernova simulation. I'm going to present, so to speak, toy problems, so smaller systems in which we can have a handle on the dynamics of the system and we can understand how to treat it. So we'll have only 2 flavors, just neutrinos, no antineutrinos. We'll start, for most of the talk, will be a constant neutrino gas, neutrino density, so to speak. To make calculations feasible, I have to discretize it. It's done on a momentum lattice. Think of it as a box quantization. In these kind of geometries, we can follow the flavor evolution of the system for a few particles. I'll go here up to 20 particles in the system, and also will explain why a few particles and what are the difficulties in going to higher systems. I will compare to the single angle, which is an approximation while still being many-body approximation, while the most common calculations we see in the literature are actually mean field calculations, mean field approximation. I'll compare to those two. At the end, I'll give some new results on an expanding neutrino gas. That is something that is a better approximation to supernovae environments. Such a thing could also be used for neutron star baryon mergers. So, in order to understand many-body treatments, first we have to create an algebra. We know that when particles are produced, we can do the second quantization language. For a given momentum mode, we can have a creation of an electron or X flavor, and also their annihilation. The algebra can be combined together to create ladder operators in an SU2 algebra of flavor. So this is flavor space. When I'm going to talk about spin, I'm going to understand by that flavor. So electron flavor or X flavor. JZ is the polarization operator, which we'll calculate later, the expectation value of this operator. This gives us the net polarization, so the net number of electron flavor versus X flavor during our calculations. The Hamiltonian. A many-body Hamiltonian is composed of many-body terms. The first is the one-body term, and then we have also a two-body term. So let's go through each of them. Please stop me, ask me, by the way, if I go too fast or if I jump over topics. The one-body term is the mass term, given here by the time squared over 2p. This is a kinetic term. It's an artistic expansion of a kinetic term with particles that have a very small mass. Theta, again, is the mixing angle. For two flavors, we have one mixing angle, which is theta. And we've written here in the operator language the one-body term. So this is just the normal vacuum oscillations of neutrinos. We integrate overall momentum modes. And also we have a force scattering with matter, which depends on the electron-neutrino number density and comes with 1 power of GF. As a simple explanation, we know that usually scattering comes with 2 powers of the coupling. Here comes with 1 power because think of this as a self-energy diagram in parentheses of just one neutrino at a time interacting with the background of matter, in this case electrons. We're keeping only leading order terms in this Hamiltonian. There are also scattering terms which come GF squared, which for now we're ignoring, but they are weaker with respect to these terms that we're keeping here because GF is a very small coupling. Because we're talking about an environment where we have a lot of neutrinos, remember we have 10 to the 53 erg, which will be 10 to the 58, for instance, neutrinos, we have scattering between them. Here consider forward scattering between neutrinos. The parameter 1 minus cosine theta of the two momenta directions guarantees that neutrinos which are parallel or antiparallel don't scatter with each other. It's a two-body term because we have two operators here. This is a vector product of two spin operators in flavor space. Also, this term is GF, so it's the same idea. You have one neutrino interacting with the other neutrinos to give a self-energy diagram. In parentheses, also we have V, which is a normalization volume, which we will understand as a parameter which is inversely proportional to the number of neutrinos. The more neutrinos I have close to each other, the more I can scatter. To make calculations feasible, we have to discretize. So instead of integrating over the momenta, we are summing over them. In compact notation, the one-body term has an omega p, which is a time squared over 2p. This is the frequency from the one-body term. B, which is a misalignment vector between the two eigenbases. Think of it as analogous to a magnetic field, to a perception of a spin with a magnetic field. Although this is flavor space, the analogy works because it's an SU2 algebra. And also we have forward scattering with matter. In addition, we have the two-body term, so we're summing over two modes here, and the two-body term we're gonna consider to be mu, which is proportional to GF over V. In this calculation that I will show today, I have not done a simulation where I've effectively evolved the supernova, so I'm not tracing how matter evolves, how the ejecta goes away from the star. So instead, I'm focusing on a constant matter background. Think of this as a toy problem in that sense, or we can also think of it as a fact that we're focusing on oscillations, flavor oscillations, which should be fast enough that for which we don't see a big variation in the dense matter profile. So we are zooming in a point of a supernova where the density of matter is almost constant. This allows us to combine together the vacuum term and the forward scattering term into an effective one-body term, which has a frequency omega bar p, as shown here, and a mixing angle alpha. The relationship with the vacuum terms are given as shown here. What this means physically for us is that if you have a high electron density in the background, your mixing angle will become very small. That is to be expected, as the more I interact with matter, the more I should be in favor basis in which the interactions with matter do happen. And also I'll have an effective one-body term which will increase. The omega p term does increase in this case. So how do we deal with this in practice? The full two-body term is given here, is neutrino-neutrino forward scattering. This is the full two-body term. All things we have done so far is to just discretize the momentum modes. While still keeping the two-body nature, so we still have two operators, we can do a single angle approximation as shown here. And instead of having the individual modes, we can sum them up together and get the total angular momentum operator as shown here, which introduces a spherical symmetry in the problem that you might not have here depending on how the neutrinos evolve. But regardless, this is still a many-body treatment. The mean field approximation, we don't need necessarily to do a single angle approximation, and I have not done one here. But instead of having two operators at two momentum modes p and q, we have a three vector p, which is a polarization vector, and an operator, which is the flavor operator. The polarization vector is the expectation value of the respective operator with a full wave function. As we can see, this is a sort of a chicken and egg problem, because to know the dynamic of the system, to know the Hamiltonian, I need to know the polarization vector at each mode. But to get the polarization vector at each mode, I need to know what the wave function is as a function of time at that specific mode. One way to get out of this is to write down the below, which is shown here. This is a consistency equation that follows this Hamiltonian, in which now I have everything written down in terms of just the three vectors, just the polarization vector. The vacuum term, together with matter here, gives us a fixed direction in space, this vector b, along which we can have a precession due to the cross product with polarization vector. And each vector in all its lattice has a cross product with the other vectors in all directions. This is what the mean field treatment gives us. There's a very interesting assumption in the mean field approximation that allows us to go from two-body operator to a one-body operator, and that is there are essentially no correlations, or correlations are too tiny to be relevant. What do I mean by that? If I take the expectation value of a product of two operators, if I don't have correlations, I should be able to factor them out, meaning to take the expectation value of each operator separately and to multiply them together. What this tells us is that the many-body wave function, for instance, of n particles, can be written down as a direct product of n single particle wave functions altogether. While if correlations are present, I cannot have such a factorization. This is an implicit approximation in the implicit assumption in the mean field approximation that allows us to write down this equation in the first place. Now, why in practice we don't see a lot of calculations in the many-body treatment in the literature? It's an inherent computational difficulty. Let me give you some quick estimates of why that is so. Let's say we have n momentum modes. Momentum modes, I mean magnitude and direction. And since these are fermions, they are particles, we're assuming that the coefficient number there can be up to 1, 0, or 1 in a given mode. So we have one particle per mode in this approximation. If we want to solve the equations of motion for the mean field approximation, we have three directions. So we have 3n coupled partial differential equations like we shown before that we have to solve. If I want to do a many-body treatment, I have a coefficient number of either 0 or 1. So I have two possible values for each single particle state. So when I write the full many-body state, it's 2 to the power of 2n. And the Hamiltonian itself would be 2 to the power of 2n. So it would be even the square of this one here. Which means that, for instance, if I have just 100 modes, which is a very small number because we need 10 to the 50 something for the supernovae, I would have 300 mean field equations, which I can do on my laptop, but I would need to have 2 to the power of 100 numbers just for the wave function itself, and a lot more for the Hamiltonian, which is more than 10 to the power of 30. Which means that in practice, if I scale up to larger and larger number of particles, it's impossible to do it in a classical computer because I won't even be able to have the memory to do this calculation, let alone evolve it. Which means that in an idealized scenario in which we had all the technical tools available to us, we would need actually a large-scale quantum computer that would be something that would allow us to do these calculations without doing any approximations, because we actually have the power to do so. In reality, we don't have that, so we can do only, for now, just small number of particle systems. But even from those, we can draw some conclusions. So what are we going to actually observe in a calculation? Now, keep in mind, this is a theoretical calculation, so we have to create some observables to compare. The polarization is actually an observable that you can match, because you can detect neutrinos on Earth and you can tell their flavor. Correlations will tell us whether we can factorize the wave function. And another, in parentheses, observable that I'll introduce to is entanglement entropy. The first two were more familiar from literature. Entanglement entropy is more common in quantum computing literature, so I will spend some time on that. Just keep in mind that both entanglement entropy and correlations are by default 0 in a mean field calculation. So just a quick example of entanglement entropy and why am I considering it for this calculation. Let's say we have a Hilbert space where our operators reside, and I decide to do a partition into two sets, co-complementary sets A and B. That's shown here. If I perform calculation, I can get the density matrix of the many-body wave function. And if I trace out, for instance, the subspace B, I come up with the reduced density matrix rho A. And for this density matrix, I can calculate the equivalent of a von Neumann entropy, that's shown here. We call entanglement entropy. Keep in mind, this is not a classical entropy. What it actually tells us is about the maximal mutual information that A and B subspaces can share. Some properties of this entropy are that both subspaces share the same value, so both entropy of A and entropy of B are equal to each other. Because this is a bipartition of two subsystems, the entropy is bounded below by 0, so there's no entanglement entropy, and above by log 2 because there are two subspaces. If I start my calculations with the many-body wave function, so let's say that I'm not doing a thermal distribution of wave functions, I just have a pure many-body wave function, then if the entanglement entropy is 0, it means there is no entanglement. What entanglement means qualitatively is that these many-body wave functions of many particles put together, these particles are entangled. I cannot factor them out one from the other, which means that if I cannot factor them out, I cannot treat them as single particle states independent from each other. I cannot do a mean field approximation. So every time this entanglement entropy is non-zero for these calculations, it means that factorization is not possible. As an example, let's take a two-particle system. So we have two particles, and we have just two states available for this particle, the ground state and one excited state. The wave function here is a sort of triplet wave function, if you think about spins. This is a well-defined wave function of two particles. I trace out one of them, and I have the following rho A density matrix, as shown here. The entanglement entropy for this reduced density matrix is log 2. It's maximal, which means that this very simple wave function cannot be written down as a direct product of two single particle wave functions. And indeed, it shouldn't, because these two particles are entangled. Of course, two particle systems being entangled is something one can expect to be so, and mean field approximations one expect to be right for a very large number of particles. We cannot go to a very large number of particles directly, so we're going to do some more in between and see whether entanglement entropy in few systems, which are not that small as two particles, actually are present and what they can tell us. So I will not go through details of how we do calculations on a lattice. I'll just want to show the results and try to analyze them. The first example, we take 8 neutrinos. This is a cubic lattice. So these 8 neutrinos have the same momentum magnitude, but they're given in different directions here. We start with a system in which 8 neutrinos have all the same flavor, the electron flavor. The plots I'm going to show will have 3 lines in them. We'll have the blue line is for the multi-angle many-body, red dashed line for the single-angle many-body, and the orange dashed dotted line for the mean field approximation, which is multi-angle mean field. On the first plot here, I'm plotting as a function of time. The time is the inverse two-body coupling units. Here I'm considering both two-body, one-body to be the same order of magnitude. I'm plotting the polarization as a function of time, which goes from minus 0.5 to 0.5. And what we see here is that we don't see 3 different lines, we see just one line because they exactly overlap with each other. So we have the same behavior for all 3 of them, and indeed, this is just a vacuum oscillation. And if you look at the correlation for the full 8-particle system, so the product of all 8 operators minus individual expectation values, properly normalized, is 0 throughout the whole evolution. What this tells us is that for a monoenergetic system, meaning they all have the same magnitude of momentum, and start with initial flavor being all the same, we only observe vacuum behavior. From the mean field perspective, this is easy to explain. What happens is that you have all neutrinos having the same flavor, meaning in flavor space, these vectors are parallel to each other, so these cross products should all vanish in this case here. But they have all the same omega term, omega p term, the same frequency, so they precess around the B field all with the same speed, therefore they all remain parallel. These cross products between them will always vanish. The two-body term should never have any effect on it. That's what the mean field tells us. Keep in mind that if the flavor is sum of them E and sum of the X, there will be anti-parallel, which means that for the mean field case, still the two-body term should not give us any impact on the flavor evolution of the system. What happens though for the many-body case? So we have the same system. Now, instead of having all of them being electron flavor, we know that in supernova we produce all three flavors, so we should expect some of them to be X flavor, two of them, for instance. On the left, I'm plotting as a function of time where both one-body and two-body terms are the same, or unit 1, while on the right, the one-body term is 5 times weaker than the two-body term. I'm plotting on the top one electron neutrino that is initially an electron neutrino flavor, and on the bottom an initial neutrino which is X flavor. What do we observe? For the mean field, again, we see the vacuum behavior in both plots, left and right. And the mean field behavior scales with the one-body term. One-body term was weaker here, so the period here increased. While on the other case, it's shorter. For the single angle case, we see rapid oscillations that agree that are with this mean field envelope in parentheses, as shown here. This tells us that we have a slow oscillation behavior, so in parentheses, slow oscillation coming from the one-body term, so just a vacuum term. And we have a modulation on top of that coming from the two-body term in the single angle. In the multi-angle case, with something interesting, because specifically for the, in parentheses, minority flavor, so the one that we have less amount of initially, we have a rapid flavor equilibration, as we see here, and then the amplitude of oscillations is close to 0 for most of the time. What this tells us is that for this specific flavor, for instance, X flavor in this case, while it initially the neutrino started being a pure flavor, X flavor, after a certain amount of time, if it interacts with matter, the flux in this direction, given by this neutrino, will be almost half of it will be X and almost half of it will be E. So it will affect how the neutrino interact with matter as we go through. These were neutrinos all with the same momentum magnitude. Let's take another case. Now we have 12 neutrinos. We have 8 of them having the same magnitude and 4 of them having a magnitude of momentum 3 times larger. A 2 ratio 3, which is what we see typically between the typical spectra of neutrinos in supernova simulations. On top of that, so we have 8 electron and 4 X initially, I decided to put them in a very dense electron background. What this means is that the mixing angle for the X flavor will be 0.03, while for the electron will be 0.01. These are very, very tiny mixing angles. Henceforth, it's an intuitive understanding that we can get by looking at the mean field, which in both cases is just a flat line, meaning there's no flavor evolution, is that if you start with a given flavor, you stay in that flavor. Why? Because you scatter with matter a lot. Interactions with matter are on flavor eigenbasis, not on matter eigenbasis, so you don't expect to have flavor evolution. Well, that's a nice intuition to have. Unfortunately, when you look at the many-body, the picture is not as simple. If you look at the both blue line, which is a multi-angle many-body, and the red line, which is a single angle, again, many-body, they're both many-body treatments, we see that specifically for, again, for the minority flavor, the one we have less of, we have again the rapid equilibration popping in. It happened in vacuum, it also happens in a dense matter background. What this tells us is that as long as we have a flavor content which allows for both flavors to be initially present, even in a dense matter environment, we will have these oscillations as we see here. Again, we have the same qualitative behavior. If you start initially with X flavor, which in this case has an energy which is 3 times higher than the energy of the electron neutrinos, kinetic energy, so it will, after a short period of time, become almost equal proportion of X and E flavor, which means that if I have a high energetic muon of tau neutrino, it might get converted into high energetic electron neutrino, which will subsequently potentially interact with matter through a charge current reaction or even neutral currents. While for the E flavor, we still have a mixing, but this is still mostly electron flavor neutrino. Again, these are small systems, so we'll have to see what happens when we go to large systems, but it's interesting that we have this qualitative difference which might have implications for supernovae. What happens to the correlations in this case? They're normalized between 0 and 1. As we see here, they shoot up to maximum value of 1 for the multi-angle case, while for the single angle many-body case, they oscillate. This is in agreement with the fact that the single angle is somehow between the mean field and the multi-angle many-body. Again, correlations are supposed to be 0 for the mean field assumption to be true, so the mean field line would be 0 here when not plotting it. The fact that correlations are not only not 0, but are pretty high in this case, is telling us that there's something happening, that this wave function, although it started being a mean field wave function initially, it changed into something more. And what happens with entanglement entropy? We are plotting here for one electron neutrino and one X neutrino versus the rest. So we take one neutrino and say, how is this neutrino entangled with the rest of the medium? If the value was 0, that would be good for the mean field. It means that we can just separate it from the rest and study it independently. Log 2 is a maximum value that it could have, which is somewhere here. And as we can see, for both neutrinos, their entanglement entropy is pretty high. It's higher for the multi-angle, and for a single angle, there's more oscillations, which was the same thing we saw for correlations. And this is, remember, in a dense medium environment. So if we have a dense medium environment, we still have entanglement shock popping in, and it's pretty high, which tells us that, unfortunately, this wave function is far from being a simple mean field wave function as a passage of time. The last numerical calculation I'm going to show is with 20 neutrinos, again in a dense medium, that's shown here. Again, ratio of 3 of momenta values. And we see a similar behavior as before. In this case, just to play around, I took the electron flavor to be 4 and X flavor to be 16. So in this case, the majority flavor is the electron flavor. But it's the same behavior as we saw before. The flavor it is least amount of in the wave function initially is the one that gets very rapidly equilibrated to almost close to 0 in the multi-angle case versus the mean field and single angle, which don't show as much of this change. That's run in both plots here. Correlations, again, are very high. For a single angle, they do oscillate, but they're still non-zero. And the same thing happens for the entanglement entropy. So in all these cases, we went from 8 to 12 to 20. Also on the archive, we can find examples with 16 and so forth. We see the same qualitative behavior, which means what? Specifically, it means that as long as I start my calculations, even though I start them with the mean field wave function, but I have both flavors initially present, I will have the so-called qualitative behavior, meaning the two-body term will give me some non-trivial behavior in which both correlations and entanglement entropy start from 0 and quickly ramp up, which means that mean field will start to be more and more off, so to speak, in these calculations. But this was done just with a constant neutrino gas and a constant matter background. Again, these are just qualitative toy examples. Supernova is much more complicated, but this gives us some interesting insights. Can we do slightly better? Yes, we can. We can try to take a neutrino gas and make it expand. That's shown here by the straight neutrino bulk model. A calculation of this type was also done in the single angle approximation in detail by Professor Balantekin, Amol, and business unit Michael. And what I find is similar to what they found there. Qualitatively, we agree, and also conjunctively. The two-body term, this coupling, starts here at value of 1, at a radius of 1. Think of this as a radius far away from the core of a supernova during a neutrino-driven wind phase, for instance. The two-body term starts being order 1, comparable to the one-body term, and it quickly drops almost to 0 in a very short radius range, and then it's almost 0 for all the rest of the calculation. So I have never considered, I've not shown here calculations in which the two-body term is much stronger than the one-body term, because then you would expect to have a collective behavior just because the two-body coupling is very strong. But I've shown that they are comparable, meaning we are in a part of a supernova explosion in which we have a dense matter background, but we also have dense gas of neutrinos, which happens close to the core, close to neutrino sphere, etc. The initial configuration will still be just the one energy, so they're all the same momentum magnitude. That's shown here. for simplifications, and we have 8 of them being electron flavor, 2 of them being X flavor. Since during these calculations, most of the time you just have a vacuum term being present there, because as we saw here, the two-body term drops rapidly. The polarization as a function of time will look most of the time like a vacuum polarization with some slight kick, so to speak. So instead of showing that, I decided to show correlations, specifically here connected correlations. So to build a hierarchy of them. This is done by the Ursel functions. Mathematically, this is the derivative with respect to the cumulant generating function, where the sigma z's are just a polymatrices. What does it mean for us? For people who are familiar with diagrammatic calculations, Feynman diagrams, at a given order in the calculations, if I were able to resum all the diagrams of a given order, I would have a result which would be equal to the Ursel function with the same number of derivatives here. So think of this as the summation of all Feynman diagrams if I have some small parameter. Here I'm doing a many-body calculation, so indeed this derivative for me will count the number of particles, the correlations for which I'm studying. So if I have a 3-particle correlation, the Ursel function with the 3 derivatives will give me the residual 3-particle correlations when I have removed all pairs, and so on and so forth. So I don't have a pollution of lower orders into high orders and vice versa. I'm going to show only a result for the multi-angle here, since quantitatively it's the same as the single angle. And I'm going to plot all pairs, all triplets, and so on and so forth. So this is the correlation for all pairs in the system as a function of radius. As we see, initially it started at 0. It's a mean field wave function initially. They grow rapidly for the very short amount of time or radius span here for which we have a two-body term present. And then they just oscillate. Meaning, even a small amount of two-particle interactions are enough to give rise to correlations which will not die down, will only oscillate. The only way to make this disappear is if I actually have a true scattering event in which I'm absorbing a neutrino and I'm re-emitting it. For which we don't have collisions here in these calculations, we're just talking about forward scattering. That's why we see these correlations which start but are present throughout the whole radius expansion. Then you have the 3 particles. These are all triplets. We see the magnitude goes down, and so forth. We can have all quartets, and so on and so forth. What we see is that the magnitude is slightly going down, not exactly monotonically, but it's slightly going down with as I have more and more particles, meaning I have more and more particles to have correlations with. Since I have 10 particles, 10-particle correlation is still present. It's small, but it's still present. What we'll do for this system, even though I have 10-particle systems, is that there's a hierarchy in parentheses of correlations. This is a small number of particles, so one has to try to increase number of particles and see where the hierarchy exists, also for higher numbers. If that exists, it would be a nice thing, because it would mean that even though I have correlations present in the system, some of them are more important than others. Specifically, 2-particle correlations are non-negligible, which is good from a computational point of view, which means that instead of waiting to have a large-scale quantum computer, which might be the case and perhaps even further along in time from us, or take the other extreme, which we say, I just want to do a mean field calculation because it's practical and I'm neglecting correlations. Well, one can do something in between, in which one can also include a 2-particle wave function where correlations are present on top of the single-particle wave functions in doing this type of simulations. Sort of a middle ground in parentheses. That seems to be indicated from this calculation, but we have to do a lot more analysis to make sure that this is actually the case. Now, why would we care in a supernovae simulation for this type of flavor oscillations? Well, they have to be relevant for the time scales of a supernovae, for instance, or even a binary merger. Otherwise, we wouldn't care, because the whole explosion happens for a period of 10 seconds, and neutrinos are very relativistic particles, which means that they travel very fast and they might leave the star before all of this happens. So let's do a 0th order comparison of time scales. The time scale for an oscillation will be inversely proportional to the 2-body term. In full reality, it's a complicated function of both 1 and 2-body terms, but just as an estimate, we just focus on 2-body term here, which is GF over V. GF is the weak coupling, and V is normalization volume, which for us is inversely proportional to the number density of neutrinos. So the denser the neutrino gas is, the more I can have a force scattering between them. A charge-current reaction depicted here is an absorption of a neutrino. This is proportional, as we know, this is an actual scattering event. It's proportional to, as we see here, the coupling squared, the energy squared, and the baryon density. The mean free paths are inversely proportional to the rates. So the ratio of a mean free paths can tell us how many oscillations I will have per between two consecutive scattering events on average. And as we see here, that if I focus on if I zoom in at a very small point in a supernova explosion, where I am considering the neutrino number density to be 1/1000 of the baryon density there, wherever that is, and I focus on the 10 MeV neutrino, which is a typical energy, neutrino energy for these environments, then I will have order of 10 to the 6 oscillations between scattering events, which means that for these densities, we have oscillations which are faster than squeak scattering rates. Of course, the neutrino density is much smaller than baryon density. The ratio will go down, but it will still be a high ratio, which means that another complication in practice on including these oscillations, which I'm going to call them fast because with respect to the speed of the scattering events, is that if we have to keep track of all as neutrinos evolve and leave the star, we have to keep track of very different time scales. And these are very orders of magnitude different from each other, the time scale for a scattering event versus the time scale for an oscillation. So it's another complication in simulations if one was to include it. So indeed, it's a very hard problem on many directions, but oscillations should matter if they are so fast. Why would they matter? Naively, one would guess that they would matter because if you have a flavor in parentheses equilibration, you could have a high energy electron flavor, which you haven't accounted for, because it was a mu or tau neutrino, which became an electron flavor at the right time for it to interact with neutrons, for instance. So, as a summary of this quick excursion into toy problems regarding supernova, we saw that for these few-body systems, if we start with a wave function in which we have both flavors initially present, we will find collective behavior. And that happens because we will have non-vanishing correlations and entanglement entropy. This is happening when you do antibody treatment. And the mean field ignores this by default, by construction. But it might have interesting implications for supernovae because the time scales might not be too slow, might actually be relevant for what happens in supernovae. And also we saw that two-particle correlations are important. So it might be a suggestion for future directions to look at two-particle correlations. From a many-body perspective, we would like to know whether this persists in the large M limit when we have the full Hamiltonian of matter, vacuum, and neutrino-neutrino scattering. Unfortunately, we can only go so far with current server computers, but that's an area that one needs to explore. Of course, one would have to include anti-neutrinos. And the neutrinos should not change relatively too much the picture. It would be an additional SE2 algebra, for instance, if you have two flavors content. Also, we have three flavors in reality, so we should include a third flavor, but that would be an SU3 algebra rather than an SU2 algebra. So all of this could be done. They will require time. The main drawback is the large n particle limit, which still evades us. But these are indications that this could be relevant. Now keep in mind that not only we're doing neutrino transport, we have to do oscillations on top of neutrino transport and simulations, and including two-body correlations might be something which might be more feasible for the near-term calculations. With this, I'd like to conclude. Thank you all. Also, my funding agency, NCIS, Network for Neutrinos, Nuclear Physics, and Symmetries. And I welcome all your questions, and please ask whatever you need. I went a little bit fast over this, but hopefully I was able to share the gist of the work. Thank you.
Yes, thank you for the great talk. Unfortunately, it's hard to applaud with everyone muted, but I'm sure it's happening. Yeah. All right, so there's lots of time for questions. If anyone wants to either pipe up or raise your hand in the participant list, and we'll start calling on people for questions. All right, Sherwood has a question.
Hey, Ramal, sorry I had to join late because of other obligations. In your conclusions, you mentioned that there's collective effects that show up with the many-body treatment, but not with the the mean field treatment.
Yeah.
Is that something that you expect to still be a strong result if the number of individual bodies is a large number?
The true answer would be nobody knows. Meaning, if I increase the number of neutrinos, nobody knows because you cannot do this. It's hard to tell because it's not just number of particles that matters, it's the neutrino number density. Meaning you could have a lot of particles, but if you just focus on a small packet, and then you have a fixed number neutrino number density there, that will tell you whether the two-body term will be relevant or not in that calculation. So you'd have to follow if the density becomes too high or it's not really that high. So you can compare the two body. So this is just a way to compare as coupling terms in the Hamiltonian two-body and one-body terms. There's another complication which comes with how does it scale as a function of particle number. That's completely unknown. So that is not something that we can tell. I understand that the common sense in the mean field treatment is that if I have a lot of particles, I should see some average behavior with the background. But unfortunately, I don't see that happening with my 20 particles. So I hope I could see something like that, but it didn't happen. It doesn't mean that it will not happen if I have a lot of particles. So that's why I'm saying it's an open question, and we don't know that. That's a future direction. Anything I would give you would be educated guess, but I don't have a factual evidence for actually answering that.
Okay, thanks.
No worries. But yeah, one comment related to that is that since we don't know what will happen, rather than saying, oh, well, once you prove that it's true, I'm going to ignore it. Well, we shouldn't do this because we're trying to do science. We shouldn't just ignore things until they scream at us that they're there. One way to do something in between would be, like I suggested, to include two particle correlations together with calculations that we already do for the flavor evolution. So it would be coupling single particle wave functions, which you already have QKEs, for instance, established for, to add another term in that which has to do with the two particle correlations. That would be something that, although not being full many-body, at least captures some features of a many-body treatment. And you can do a systematical study in which, if the two particle included that way and stopped so consistently in that treatment, it's not too small. That tells you that in a full treatment, perhaps that would not be small at all. If it's very small, maybe you could ignore it for now. So it won't be a way of deciding yourself whether you should worry about many-body effects for the time being until you can actually do a full on-computing calculation.
Would this be equivalent to a two-loop contribution to the potential?
It's not really a two-loop. It's more. Okay. It's more if you you have a density matrix there, which is a Fermi distribution sorta in equilibrium, right? The one particle. You have a rho 1, 2, so to speak, which is not a product, which is equal to rho 1 times rho 2. You have the rows individually already, plus C1, 2, which is a connected term. It will be another function on top of the rows that you have in the QKEs. So it will be something like that.
Okay.
Yeah, yeah. So instead of having a product, you have a product plus something else. And that something else will appear on your left side and slightly also on your right side of the QKE. Yeah.
Okay.
If I can chime in for a second, sure, but two-loop contributions are temperature dependent explicitly. And this whole treatment is, of course, does not depend on temperature.
Yeah. Well, if you have temperature, you have a much complicated initial conditions, right? You don't have just one pure wave function. So, but regardless, even if you start with just a pure wave function, we do see these effects, right? So.
Other questions? I have a question,
yeah.
if there's sort of a gap here. I was curious if you have any intuition. So the sort of collective supernova simulation or approximation you did sort of assumes the spherical symmetry. Do you have any intuition about what would happen if you have something like a neutron star merger where the symmetry or lack thereof between the neutrino emissions is very different than for a core collapse supernova environment?
Yeah, that would be interesting. That would be a very interesting setting. Because there you have emission of neutrinos, but it's not, I mean, it's not homogeneously all the way, right? So you'd have certain directions in which neutrinos are very sparse, so to speak, in parentheses, in terms of density. So for those, mean field would be fine. And then you have other directions which you would focus your many-body treatment, if you could do both, right? So you could say, I'm going to focus my computational needs here in this right small angle direction that I know I have a lot of neutrinos per cube. So it'll be something like that there. It'll be slightly easier in that sense, but I don't know. Nobody has actually done calculations to see.
True, yes.
Yeah. But yeah, that would be also interesting in itself. And there probably you don't have to worry about as much about matter ejecta popping in your system as here. You potentially could find cases where you could just ignore the matter background and say it's just a vacuum plus neutrino scattering. Yeah. I mean, I know I went fast over this. So any questions even for the introduction, whatever you have, I'm happy to answer. I'll just go to the beginning.
We have another raised hand. Go ahead, Mark.
Hello, I cannot hear you.
Okay, can you hear me now?
Yes. Yes.
Okay, great. So in your conclusion, you had the time scale going like V over G Fermi.
Yeah. Yeah.
So is V the volume?
Yes. It's
so what?
Yeah.
So why does it go like the volume and yeah, why?
Yeah. Okay. Yeah. That's a really good question because in this. I think the slightly revert, by the way. Can you just mute quickly and then yeah, thank you. So that's a really good question. If you look at the Hamiltonian, I'll try to go to the original Hamiltonian. The two-body terms comes with a coupling which is GF, which makes sense, and this V. This is in the literature. I've seen everywhere this V, and they think of V as a normalization volume. What physically this means for me is that this is inverse number density of neutrinos. And if you put inverse number density of neutrinos here, so if you multiply this GF by the number density of neutrinos, you have the right units, and physically it makes sense. It's telling you if I have a lot of them or few of them. So think of this V as inverse number density of neutrinos. In the literature, they put V there. So I went with the calculations in the literature, but that's how I give it a physical meaning to this system, right? Because you don't want an extensive property in a coupling in Hamiltonian. That would be weird. Yeah.
Can I chime in again, Mark?
Sure.
This is Baha again. You know, in field theory, one deals with Hamiltonian densities, Lagrangian densities. If you go to that, then there is no explicit volume dependence because everything depends on densities of these J's or neutrino densities and so on. The reason that the volume appears explicitly is because we write the Hamiltonian rather than Hamiltonian density. And at the end, the volume should disappear from any physical calculation.
Yeah. Hopefully. If it disappears, it means that you captured the thermodynamic limit properly. So think of it as an inverse number density for all intents and purposes here, which is what I do when I do the time scales. Where is it? Yeah, I think I have it at here. Yeah, so here I'm writing, instead of V, I'm just writing number density of neutrinos. The large N limit will tell you if you have a numerical prefactor here that multiplies with GF over V, which goes up or down as a function of number of particles. That's what the large N limit means, and that's something that we don't know, which might affect what this number here actually is when you want to compare to charge current rates, which was a question that also was posed earlier.
Any more questions?